Scientific measurements. We make a lot of measurements in science. We measure length and time and volumes and masses. We report those measurements in a very particular way. We report them so that every digit that we write down is certain plus one estimated digit. So as an example, I leave these just to make up on the spot, and sometimes I'm better at that than other times. If I write 2.5 feet, I am certain that it's at least 2 feet, and I'm saying I'm estimating that it's halfway between 2 feet and 3 feet. If I write 2 feet, there's only one digit. That's the estimated digit. I'm saying it's about 2 feet. It's more than 1 foot, less than 3 feet. If I say it's 2.50000 feet, then I'm saying I'm certain out to this decimal place. This one's estimated, but all the rest are certain. It's important to understand how scientists write down numbers. If we write down something with lots of digits, we are more confident in that measurement. The confidence in the measurement comes about by how it was measured, what kind of a measuring device was used. Your book has an ongoing thing about carbon monoxide in the air. Here are two different tables. This one is giving concentrations with 1 decimal point, 8.9 parts per million. Well, we wouldn't want to take these numbers here, this data, and round it off, 9, 6, 5, 3, and 2. We're throwing away information. So scientists are very careful about which digits they write down. And I'm going to expect that out of you, especially in lab. Yeah, close the door. The Amtrak trains are so polite, and the freight trains are so obnoxious. So how do we know how many digits to write down? It depends on the measuring device. And the phrase to remember to help you to do this is read between the lines. So if we look at this balance, and here's the little measuring mark, and this is 0, and this is 1 gram and 2 grams. We're looking at these little lines here, and we're seeing that this one's 10 grams, this one's 0 grams. There's 10 lines in between. That means each line is 1 gram. Well, we can see that this black mark, which is moving relative to the mass of the pistachio, is definitely above 1 gram. There's no uncertainty in that. We will all agree on that. And so we write 1 gram, but then we estimate, we read between the lines. And this is an estimate. People will disagree on what it is. The author says, I'm estimating it at 1.2 grams. You might disagree and say, no, I think it's 1.1 gram or 1.3. There's uncertainty in the last digit. So what we do is we estimate 1 decimal place past the smallest division. On a thermometer, a ruler first. If the divisions represent 0.1 centimeter, then I estimate 0.01. If the divisions on a thermometer are 1 degree, I'm going to estimate 1 decimal place past that. You will get this straight in your head by practicing and checking that you're doing it correctly. Let's look at these. These are nice and blown up so we can see them. So this is a thermometer. They're asking us to record the measurement with the correct number of digits. So here's the red alcohol, and the end of it is kind of hiding behind that 100, but it's right here. And so we look here, this is 90 and this is 100. So each of these smallest divisions is equal to what? 1 degree. So the smallest division equals 1 degree Celsius. Well, the end of this. I'd say it's pretty clear that it's 103 and maybe a smidge over. Anybody disagree with that? 103 is certain. We're going to estimate the next place. So 103, the 3 corresponds to the smallest division. We need to go one place further. So I need to go point something. What do you think? 0.1. That's good. I heard somebody say 0.2. That's okay. You might think, well, I think it's right on 103. Then you would write 103.0 degrees Celsius. Any questions about that one? Yes? How do I know it's Celsius? I'm just pretty sure it is. It doesn't say on there that it is. That's a good question. Yeah, in science we use Celsius. I always laugh when I give a lab practical in 3A and ask people to measure stuff and they do it in inches. Then they're trying to do significant figures with fractions and it's just really, really ugly. Just don't use inches. Everything is going to be metric. Here is a graduated cylinder with a clear liquid in it. When we measure liquids, there's a meniscus. And we'll learn why it does this later. It has to do with surface tension and adhesion. But there's always a curved surface. We measure the bottom of the meniscus. That's how all the glassware has been calibrated, is for the bottom of the meniscus. So we look at this curve, and we see that it's just a little bit below this white line. We need to figure out, what does each of those smallest white lines represent? This is 4, and this is 5. So each of these must be 0.1. So here, I'll just call smallest division is 0.1. Now, again, with the unit doesn't show on the picture, does it? What do you guess the unit is? Milliliters. So the unit is most likely milliliters. So it's 4.5, as someone said, 4.5, and then it's between the 5 and the 6. So we're all going to agree on 4.5. Okay, over here said 4.56 milliliters. That's fine. I think it's 4.58. Anybody else want to throw one in there? Maybe you think it's 4.59. That's fine. The last digit is uncertain. It's estimated. There's information there, and we don't want to throw away information. Significant figures. You guys done sig figs before? If you haven't, come see me during lab and I'll help you extra. So the precision of a measurement depends on the instrument that's used to make the measurement. We just saw that with the graduated cylinder and the thermometer. When we do calculations, funny things can happen to that precision. When we divide or multiply or add things together. We do not want the precision to change just based on us doing math. And so one way to keep track of the precision in a measurement is to use significant figures. This is not the most rigorous way, maybe not even the best way, but believe it or not, it is the simplest, more straightforward way. The more rigorous way is to use differential calculus. I'm guessing that most of you would prefer not to do that. I would prefer not to do that. I learned it once and then I promptly forgot it. So I don't want to dig that up. So we use something called significant figures. They're also known as significant digits. These are the non-place-holding digits in a recorded measurement. They include all the certain digits and that one estimated digit. The more significant figures you have, the greater the certainty of the measurement. So we have a set of rules to help you count significant figures. These two columns are the examples. So the first rule is all non-zero digits are significant. So the non-zero digits in this number are 1, 3, 3, and 1. That one's a 0. So any number that's not 0 is going to get counted always. Interior zeros. Zeros that are between non-zero digits are always significant. Here's an example of an interior zero. These zeros are also interior zeros. These zeros up here are not. They're coming at the beginning. Those are called leading zeros. Leading zeros lead the number. They come at the beginning. They are not significant. The only reason we write them is to hold the decimal place. So this number, 0.00023. If we didn't have zeros in there, the best we could do was 0.23 or leave some spaces, but it would be very confusing. Those zeros do not reflect measurement. They're just holding the decimal place, and so they're not considered significant figures. The trailing zeros are what really mess students up. Trailing zeros come at the end. The way I'm describing it here is slightly different than the way your textbook does it. The outcome is the same. So pick which approach makes more sense to you. Trailing zeros are significant if there's a decimal point written in the number. It actually has to be written. So it's actually written in the number. In this number, I'm sorry, I'm in the wrong line. This number, 120.00. There's a decimal point. These zeros are at the end, but they're going to be significant because we put the decimal point. This number, 29.310, trailing zero, there's a decimal point in the number, we're going to count it. I missed these guys. 39.0, again, there's a decimal point. 1.432000. The only reason we would write these zeros at the end is because we meant them. They're not holding a place. We're saying this is a measurement. We're certain of all of these, and here's this last uncertain one. Trailing zeros before an implied decimal point. It's not actually written. You know it would be there, but it's not written. These are ambiguous. We should avoid using these kinds of zeros. But sometimes we're confronted with them, and we have to decide, significant or not. So we're going to be more conservative and say, no, they're not significant. 300. We all know where a decimal point would be if we had to put one. It would be after the last zero. But there isn't one actually written. So we look at the number 300, and we're not sure. Is the 3 the estimated digit? And they're saying it's between 2 and 400. Is the tens the estimated digit or the ones place? If the ones place is the estimated digit, then it's a much more precise number that's between 299 and 301. If we wanted to write that, we would write 300, and we would actually put the decimal point there. That would tell us that this digit is significant, and this digit is significant. This number, 100,000, we don't know. So we're going to assume the worst, and we're going to say all of those are just there to hold the decimal place, and this one as well. Any questions? Yes?
How would we know that the 10th place is significant without scientific notation?
How would we know that the 10th place is significant without scientific notation? So let's say this was 300 and we meant that it was to the nearest 10. You could do it like that. You could say 300 plus or minus 10. Another way is to underline the uncertain digit. But both of these are kind of not great. The best thing is to use scientific notation. If we put that in scientific notation, if you have trailing zeros, you will always have a decimal point. And so the ambiguity goes away, and you can specify any place to be the last significant digit. Any other questions?
Is that what you're going to want us to do?
That's what I would like you to do, yes.
So for 238, it's going to be 238.1 times 10 to the 38.
Yeah, so how would we write this one? Let's say, again, we're trying to indicate that the tens place is certain. When we put it in scientific notation, the decimal point goes after the first non-zero digit. So we get 2.3810 times 10 to the 5. We don't have to write this 0 to preserve the value of the number. If we write it here, we're writing it because it's a significant figure.
But this is the way you're going to want us to do it in the future?
Scientific notation is never wrong. It's always, if you're not sure, put it in scientific notation or show me both of them. Yes?
Okay, the reason I asked that is because, let's say it was 300 degrees Kelvin, and would you want temperatures in scientific notation too, or can you leave it ambiguous?
Well, if it was 300 Kelvin and you meant that it was to the nearest 1, you can do this and put a decimal point there and say, okay, this is 300 Kelvin and I mean it to the nearest 1. But yeah, sometimes we end up doing 3.0 times 10 to the 2 Kelvin, and that's fine. That's absolutely fine. Let's do some examples. Oh, I guess we have to talk about exact numbers. There are some numbers that are exact. And so in terms of significant figures, we would say that they have an infinite number of significant figures. These are exact counting of discrete objects. How many fingers am I holding up? 4. Is there any uncertainty? No. I left my thumb down because somebody will argue that it's not a finger. But there's exactly 4. So there's no estimated digit. It's exact. Now, how many shoes am I wearing? 2. It's exact. There's no uncertainty. So exact counting of discrete objects. Integral numbers, that means integers, whole numbers that are parts of equations. Those are exact. And certain defined quantities. Some conversion factors are exact, others are not. If you are within the metric system, comparing volume to volume or mass to mass in different units, those are exact conversion factors. If you are within the English system, there are exactly 12 inches in 1 foot. But when you go back and forth between the English and the metric systems, most of those units are not significant. Most of them are not exact. The one exception is inches to centimeters. So 1 inch is exactly equal to 2.54 centimeters. They actually redefined the inch so that it was exactly equal to 2.54 centimeters. Here are the examples. How many significant figures in each number? 554 kilometers. 3. There's 3 non-zero digits. 1.01 times 10 to the 5th meters. 3. When we look at this, the times 10 to the is the decimal place holder. These are not significant digits. In scientific notation, everything in this coefficient at the beginning is a significant figure. How about 1.4500 kilometers? 5. So 1, 4, and 5, easy. The zeros are what mess us up. Trailing zeros, there's a written decimal point, so we count them. 7 pennies, infinite. We can count 7 pennies exactly. So we would say there's an infinite number of significant figures. 0.00099 seconds. I've heard 5 and 2 and 6. 2. These zeros come at the beginning of the number. They're holding the decimal point. What happens to that number if we put it in scientific notation? In scientific notation, we take this decimal point and we move it 1, 2, 3, 4 places. I get 9.9 times 10 to the minus 4 seconds. What happened to the zeros? Well, they're in this 10 to the minus 4 now. Those zeros were only holding the decimal place. They're not really reflective of measurement, so they're not significant figures. In scientific notation, we see, yeah, there's 2. 21,000 meters. We need to assume the least precise, and so we're going to say there's 2. We don't know if someone measured that to the nearest meter, or if it's just kind of an estimate about 21,000 meters. Any questions? When we do calculations, the result has to reflect the precision of the starting measurements. We can't be gaining or losing precision, and so we have a set of rules for calculations. Multiplication and division are related operations, and they have the same rule. The result carries the same number of significant figures as the factor with the fewest significant figures. So let's look at a couple of examples here. We've got 1.052 times 12.504 times 0.53. We do it on our calculator and we write down an answer. To find out how we should round that number, we're going to identify how many sig figs does each of these things have. 1.052. That's an interior 0. We're going to count it. So this has 4 sig figs. 12.504 has 5 sig figs. 0.53 only has 2. Then we're going to look at these and figure out which is the smallest. Which is smaller, 4, 5, or 2? Well, the 2. That tells us that our answer should only have 2 significant figures. So we're going to keep the 6 and the 7, and we're dropping the 2. We'll talk about rounding in a minute, but 2 is less than 5, and so we just drop everything off. In this example, we're dividing. This is the number that the calculator gives us, 2.0035. This has 5 sig figs. This one has 3. 3 is smaller than 5. We need to round this to 3 sig figs. The 0 before the decimal point, we always write because it calls attention to the decimal point. So in science, you'll see people always put a 0 before. 0 point, it's not a significant 0. 626, the next number is a 0. We drop it off, and this is how we report our answer. In adding and subtracting, which are also related but different than multiplication and dividing, it's got a different rule. The result carries the same number of decimal places as the quantity with the fewest decimal places. I think it's most helpful to stack the numbers up like you were going to do adding without a calculator and see what happens. Let's look at this number, 2.345. Which of those digits is the uncertain digit? 2, 3, 4, or 5? The 5. It's always the last digit in a measurement. 0.07. Well, it's going to have to be the 7. And in 2.9975, the 5. There's uncertainty in the last digit. What we're doing here is we're looking at these numbers from left to right, and we're finding the first column that has an underlined number in it. That's this hundredths column right here. And we drew a line all the way down. Do the addition, write everything out. That line tells you where your number should stop. This first number has 3 decimal places. This has 2 decimal places. This has 4 decimal places. The answer has the same number of decimal places as the quantity with the fewest. So this is going to be 5.41. Here's an example with subtracting. Again, it's the last digit that's uncertain. We do the subtraction on the calculator, we get this result. Now we're going to look, the ones place, there's nothing underlined. The tenths place is underlined. So I'm going to draw a vertical line just to the right of that, and that's where my answer ends. Here's the 0.6. The next number is 7. That means that this number is closer to 5.7 than it is to 5.6, so we're going to round up. Rules for rounding. If that leftmost digit, that first digit that you're dropping is 4 or less, you just drop it off. If it's 5 or greater, you round up. We're not going to do the odd even thing that some people do. This is important. When we round a number, we do not change its magnitude significantly. So if you're rounding tenths, hundredths, thousandths, it's not usually a problem. If you're rounding in the tens place or the thousands place, students tend to lose their common sense and write some silly things. So let's say you're going to buy a used car for $12,956. But we need to round this to the hundreds place. So, I'm going to change this because I don't like how this is going. There. I don't want to make it worse. We need to round it to the hundreds place. Is that going to be $124? If I was buying a car from you and your list price was $12,356, and I'm saying, well, let's just, I only have $100 bills. Let's just round it to the nearest 100. Here, I'll give you $124. You gonna be okay with that? No, that's silly. What should it be? 12,400. 12,400 is very similar in size to 12,356. But this happens a lot when students are rounding, a density or, a number of atoms or something. They do crazy things like this. When you're rounding to tens, hundreds, thousands, what I recommend that you do is put the number in scientific notation first and then round it. Because what we had to do here was put in place-holding zeros. And that's what students forget. When you're rounding in scientific notation, you don't have to do that. So in scientific notation, this would be 1.2356 times 10 to the 4. And if I'm rounding it here, all I have to do is I say, well, the next digit, this first one I'm dropping is 5 or greater. I have to round up 1.24 times 10 to the 4. And I haven't made a big error. So if we are rounding these numbers to two significant figures. 5.37 rounds to 5.4 because the next digit is 5 or greater. 5.34 rounds to 5.3. The idea here is that we're going to the closest number. 5.35 gets rounded up. 5.349 gets rounded down to 5.3. We're only looking at the first digit. We don't have to do anything with the 9. Sometimes students start at the end and they'll round up and down all the way back. This is way too much work, and sometimes it gets you the wrong answer. So it's only the first digit you have to look at. Ignore the rest of them. Very frequently we do multi-step calculations. It's not just adding some things. We're going to add it, and then we're going to divide, then we're going to multiply by something else. Multi-step. So what we want to do is avoid any rounding until we're at the very end. If we round at each individual step, we can introduce error into the final result, and we want to avoid that. So do not round intermediate steps. Many things you can put together in a way that you can put the whole thing into your calculator at once, and you don't have to write down anything. Sometimes you have to write stuff down. When you write stuff down, keep track of the significant figures and include a minimum of 2 extra digits. So in this example here, they're multiplying these, and this is a quantity where we have 5.489 minus 5.01. Well, when you just do the math on your calculator, you come up with 19.1707. But we have mixed subtracting and multiplying, and we have to look at each of those separately to identify where the significant figures are going. When we do this subtraction, we get this result, 0.479. The rule for subtracting has to do with number of decimal places. This has 3 decimal places, this has 2. So this result only has 2 decimal places. We underline that last significant digit. So we've kept track of it. Now when we multiply this one and this one and this one, this has 3 sig figs, this has 4. How many significant figures does this one have? 0.47 underlined 9. 2. That's going to limit the answer, and so that's why we round the answer to 19. Any questions?
You wouldn't round it up though, would you? Like 4.8 or?
No, you don't want to round this to 0.48 because you're not finished. And that can cause error in your final result. Pardon me? Yeah, you'll get a rounding off error. Sometimes they cancel each other out, but sometimes they add on to each other, and we're just not going to go there. Okay, so let's do these. The first thing is just do it on your calculator. 3.10007 times 9.441 times 0.0301 divided by 2.31. I'm just going to write down everything that my calculator gives me. Anybody else get that? Cool. What's the rule for multiplying and dividing? Least number of sig figs. So we're going to look at this one. How many sig figs? A bunch. It's like, well, if we get it, we're going to count as 6. How many of this one? 4. And this guy? 3. And the last one? So how many sig figs should our final answer have? 3. So not the 0. 1, 2, 3. I'm going to round off here. I look at the next digit, the 3, and that tells me to round down, and I'm going to report my answer as 0.381. Letter B is adding and subtracting. 0.881 plus 132.1 minus 12.02 equals 120.961. Here we're looking at number of decimal places. This has 3, this has 1, and this has 2. So this is the smallest number of decimal places, 1 decimal place. I need to round my answer so that there's 1 decimal place. The next digit is 6. I need to round up. That makes this 9 into a 10 and bumps the 0 up to a 1. So I get 121, but I need a decimal place. I need to include the point 0. Common mistake is leaving off the point 0. Here we have multiplying, dividing, and adding. There's different approaches. One is to just do the math first. And make sure you know how your calculator does orders of operation. I'm coming up with 1.174,270,399. Anybody else?
Yeah.
This one's more complicated because we have 2 things going on. So we have to look at the result of this adding. The number of significant figures can change significantly when you're adding or subtracting. You can end up with way more than you started with. So I need to go back to my calculator and do that part separately. 44.11 plus 1.223. The result there is 45.333. I wouldn't want to round that, but I need to know how many significant figures it should have. We're adding, so we're looking at decimal places. 2 decimal places, 3. So this has 2 decimal places. That tells me that this number has 4 significant figures. And this one has 4, and that one has more, 5. So then my answer should have 4 significant figures. The 2 is less than 5, so I drop it off, 1.174. Letter D. 12.01 times 0.3 plus 4.811. Well, do it on your calculator, write down the answer. I get 8.414. Anybody else? We need to look at the individual steps. Here we have multiplying. So the 12.01 times the 0.3. That quantity is 3.603. How many significant figures does it have? 1. 0.3 only has 1 significant figure. And so that result only has 1 significant figure. When I add this number to that number, this ends in the ones place, this ends in the thousands place. This has 3 decimal places, this has none. So my answer needs to end in the ones place. And so my answer is going to be 8.
So is it always if the precedent is the one that has the least amount, or?
It's always limited by the one with the least. The difference is multiplication, division is the least number of significant figures. Adding and subtracting is the least number of decimal places. So it's always least, but least what? Any questions? Yes?
For example, for B, what if one of them doesn't have decimal
What if one of them doesn't have decimal places? So let's change one up here. So like if this was just 12, like that. So we've got 0.881 plus 132.1 minus 12. We write down what the calculator says. And then we look. There's 3 decimal places, 1 decimal place, 0 decimal places. So then our answer will have 0 decimal places. What's kind of tricky about the way the book talks about this is, what if the uncertain digit is in the tens or hundreds or thousands place? So another way to think about it is, what is the error on this measurement? If I'm looking at this, the last digit is in the 3rd decimal place. We assume, unless told otherwise, that that's plus or minus 0.001, whatever the last decimal place is. 132.1 would be to the nearest 0.1, and 12 would be to the nearest 1. We write 12, it's 12 feet. We're implying that it's 12 plus or minus 1 foot, between 11 and 13 feet, right? So what we're really doing is we're looking at which of these numbers has the largest possible error. Plus or minus 1 is the largest error. And so then our answer needs to be written to plus or minus 1. So we're going to keep the ones place, we're going to round it off, and we're going to end up with 121 as our answer. Any other questions? Accuracy and precision. Accuracy refers to how close the measured value is to the true value. Precision refers to how close a series of measurements are to each other, or how reproducible they are. So this is a little bit like shooting at a target. And if you are accurate, your arrows, oh, those arrows aren't big enough. Your arrows are going to be in the bullseye. That's accuracy. If I'm getting all my arrows in the bullseye, they're very close together, that's accurate and precise. But accuracy and precision don't always go together. You can be very precise, but inaccurate. This person's really good at missing the mark by this much. Very reproducible, but not right. What's more common is that you'll have poor precision. Poor precision often means poor accuracy, but sometimes if you do enough and you average all of those together, you can come up with the true value very accurately, even though your precision was poor. Let's look at 3 students, A, B, and C, who weighed a lead block over and over again. They're all doing this with the same lead block. We know that the true mass is 10.00 grams. Student A gets 10.49, 9.79, 9.92, 10.31, averages them together with a value of 10.31 as their answer for the mass. Student B, these answers are much closer together, but the average is even further away. And then there's student C, 10.03, 9.99, 10.03, 9.98. Average of 10.01, very close to the true value. Another way to look at numbers like this is in a graph. A lot of times a table of numbers doesn't really mean much. Here's the same data graphed. Here we have the mass, and the trial number. For student A, we see that this person's masses are all over the place. There's a lot of difference in the masses. And so that variation tells us this is not precise. The average is shown here in the pink line, and that is significantly above the true mass, which is the blue line. So it was not precise either. This student is much more consistent. All of the values are close together, precise. But the average is well below the true value, and so it's inaccurate. And student C nailed this experiment, and the values are close together, and the average is close to the true value. We want to be accurate and precise when we measure things in lab. What can cause us to have errors? There are two kinds of errors. There's random error and there's systematic error. Random error is, like its name, random. Sometimes your value that you're measuring will be high, sometimes it will be low. We can get rid of random error by doing measurements multiple times. Because some error is high, some error is low. When we average the results, the random error cancels itself out. So that's why we'll often do 3 or 4 trials of something in lab. Systematic error is an error that tends either to be too high all the time or too low all the time. You can be really precise but have serious systematic error. If your balance isn't calibrated, if you're reading your graduated cylinder incorrectly, your results may be precise, but the accuracy is going to be wrong because you have a systematic error.